Welcome back to AI.Code.Cast. Today we're diving deep into a problem that might seem pretty simple at first glance,
Yeah,
but trust me, it's got some hidden depths.
definitely.
Think of a spreadsheet, like a matrix,
Okay.
filled with numbers,
All right.
but with a twist.
It's not just any spreadsheet. It's kind of like organized chaos.
Okay.
Each row is sorted from smallest to largest,
Yeah, okay.
and the first number in each row is always bigger than the last one in the row above it.
Okay, so it's like a staircase of numbers.
Yeah, you could think of it that way.
Okay, but where's the challenge in this?
The challenge is in finding a specific number, our target,
Okay.
within this matrix,
Okay.
as quickly and efficiently as possible.
Okay.
And to make it even more interesting, let's add some constraints.
All right.
The matrix can have up to 100 rows and 100 columns.
Oh, wow.
And the numbers can range from as 10,000 to plus 10,000.
So we're not just looking for a needle in a haystack.
Right.
We're looking for a specific needle in a very particular organized haystack.
Yeah, exactly.
Now I'm intrigued. Where do we even begin?
Well, the most intuitive approach is what we call brute force.
Brute force. Okay.
It's like searching every nook and cranny of that haystack without any strategy.
Okay, so we go row by row,
Right.
cell by cell,
Yeah.
checking each number against our target.
Exactly. If we find a match, great, we're done.
Okay.
If not, we keep going until we've checked every single cell.
That sounds pretty tedious.
Yeah.
And probably not very efficient, especially if we're dealing with a massive matrix.
You're absolutely right. Brute force is simple to understand and implement,
Okay.
but its time complexity is OMN,
Okay.
where men is the number of rows
Okay.
and n is the number of columns.
Okay.
This means that in the worst case scenario where the target isn't there,
Okay.
we have to check every single cell,
Right.
and the time it takes grows proportionally to the size of the matrix.
So the bigger the matrix,
Yeah.
the longer it takes.
Big-
Not ideal for those time-sensitive situations.
Right.
There's got to be a smarter way to approach this, right?
Absolutely. The fact that our matrix is sorted gives us a huge advantage.
Okay.
Instead of blindly checking every cell,
Yeah.
we can use a technique called binary search to strategically eliminate large portions of the matrix with each step.
Binary search.
Yeah.
That rings a bell.
Yeah.
It's like searching a dictionary.
Right.
You don't start at A and read every word until you find the one you're looking for.
Yeah.
You jump to the middle
Exactly.
and keep narrowing your search based on alphabetical order.
That's the perfect analogy. But how do we apply that to a two-dimensional matrix?
Yeah.
That's the real puzzle here.
That is a good question.
Yeah.
If we think about the dictionary example,
Right.
we're essentially using the fact that the words are sorted alphabetically
Yeah.
to quickly eliminate half of the words with each
Oh,
step.
exactly.
So is there a similar way to divide our matrix in half with each step?
Well, remember, each row is sorted,
Yeah.
and the first element of each row is greater than the last one above it.
Okay.
Could we use that property to our advantage?
I see where you're going with this. It's like those rows
Yeah.
are giving us a starting point.
Right.
If our target number is greater than the last element in a row,
Yeah.
we know it can't be in that row or any of the rows above it
Exactly.
because of how it's sorted.
Precisely.
And if our target number is less than the first element of a row, it can't be in that row or any of the rows below it. We've just eliminated a whole chunk of the matrix in one go.
Exactly. That's the key insight here.
Okay, now we're talking. This feels like we're onto something much more efficient than brute force.
Yeah.
But how do we actually implement this binary search in a 2D matrix?
Yeah.
It feels a bit more complex than searching a simple sorted list.
It is a bit more nuanced,
Okay.
but let's break it down.
Okay.
There are actually a couple of different ways we can leverage binary search here,
Okay.
each with its own strengths and weaknesses.
Oh, a coding showdown. I love it. Let's explore these different approaches. What's the first one on our list?
The first one we'll call the two-stage binary search.
Two-stage. Sounds intriguing. What's the strategy here?
So with a two-stage binary search, we're essentially using binary search twice
Okay.
to narrow down our search space.
So like a double whammy of efficiency.
Exactly. Imagine we're trying to find the number 15 in our sorted matrix.
Okay.
The first stage focuses on finding the row where 15 could exist.
And we can do that because each row is sorted. And the first element of each row is greater than the last one above it.
Precisely. So we start with a binary search
Okay.
on just the first column.
Right.
We find the middle element of that column
Okay.
and compare it to our target, which is 15.
Let's say their middle element in the first column is 10.
Okay.
What happens next?
Since 10 is less than our target, 15,
Right.
we know that 15 can't be in that row or any of the rows above it because
Okay.
of the way our matrix is sorted.
So we've effectively eliminated half of the rows in just one step.
Right. We then shift our focus to the bottom half of the matrix
Okay.
and repeat the process. Find the middle element of the first column in that remaining portion
Okay.
and compare it to our target.
And we keep doing this,
Yeah,
narrowing down our search space by half with each comparison
exactly.
until we find a row
Yes.
where the first element is less than or equal to our target,
Right.
and the last element in that row is greater than or equal to our target.
That's it. Once we've found that potential row,
Okay.
we move on to the second stage of our search,
Which is?
another binary search.
Okay.
But this time, it's within the row we just identified. We're now searching a simple sorted list.
Okay, so in our example,
Yeah.
if we found that the third row has a first element of 12
Okay.
and the last element of 18,
Yeah.
we'd then do a binary search within that row to see if 15 exists.
Exactly.
Mhm.
By combining these two stages of binary search, we take advantage of the unique properties of our sorted matrix to achieve much faster search times compared to brute force.
This two-stage binary search sounds incredibly efficient.
It is.
But before we move on, I'm curious, what's the time complexity of this approach?
So the time complexity is O log m plus log n,
Oh.
where is the number of rows and n is the number of columns.
Okay.
In the first stage,
Yeah.
we perform a binary search on the first column,
Okay.
which takes O log m time.
Okay.
Then we perform another binary search on a single row,
Right.
which takes O log n time.
So we're essentially adding the time complexities of the two binary searches.
Exactly.
And since logarithms grow much slower than linear functions,
Yes,
this is a huge improvement over the OLAV complexity of brute force.
absolutely. Especially for large matrices.
Yeah.
The difference in speed can be significant.
Okay, so we've got one elegant solution down.
Yeah.
You mentioned there's another way to use binary search in this scenario.
Right.
What's the other approach?
The second approach is, it's a bit more mind-bending.
Okay.
We call it the single binary search on a flattened matrix.
Flattened matrix. Now you've really piqued my curiosity. How do you flatten a 2D matrix?
It's more of a conceptual flattening.
Okay.
Imagine taking all the rows of our matrix and stitching them together end to end,
Cool.
creating one long sorted array.
Right.
We're essentially treating our 2D matrix as if it were a 1D array.
Okay, I'm visualizing it.
Yeah.
So instead of having rows and columns,
Right.
we just have one long sequence of numbers.
Exactly.
But how do we maintain the connection to the original matrix structure?
Right.
If we find our target in this flattened array,
Yeah.
how do we know where it actually lives in the original matrix?
That's where some clever math comes in.
Okay.
We can use a formula to map the index of an element in the flattened array
Okay.
back to its corresponding row and column in the original matrix.
So it's like a decoder ring.
Yeah.
We're performing a binary search on this simplified flattened array,
Right.
but we have this secret decoder to translate the result back to the original matrix coordinates.
Exactly.
That's brilliant.
It allows us to leverage the speed and efficiency of binary search on a sorted array
Okay.
while still working within the constraints of our 2D matrix.
All right, I'm following the concept,
Okay.
but I'm eager to see how this mapping actually works in practice.
Sure.
Can we walk through a specific example?
Absolutely. Let's say our matrix is 5 rows by 4 columns,
Okay.
which would give us 20 elements in our flattened array.
All right.
If we find our target at index 12 in this flattened array,
Okay.
we need to figure out which row and column that corresponds to.
Okay, so index 12 in our flattened array.
Yeah.
How do we decode that?
We can use integer division
Okay.
and the modulo operator to
Wow.
do the mapping. To find the row, we
Uh-huh.
divide the index in the flattened array, which is 12 in this case,
Right.
by the number of columns in the original matrix, which is 4. The result of that integer division gives us the row number.
So 12 divided by 4 is 3.
Right.
That means our target is in row number 3.
You got it. Now, to find the column,
Okay.
we use the modulo operator.
Right.
We take the index in the flattened array,
Oh.
12,
Yeah.
and find the remainder after dividing by the number of columns, 4.
F modulo 4 is 0.
Yes.
So our target is in row 3, column 0.
Exactly. It's like
Yeah.
a magic trick.
Yeah.
But it's all based on simple mathematical operations.
Right.
We've successfully mapped the index in our flattened array
Yeah.
back to its original location in the 2D matrix.
This is truly an elegant approach.
It is.
It seems like it would be very efficient,
Yeah,
especially when dealing with massive matrices.
it is very efficient.
What's the time complexity of this approach?
The time complexity of this approach is O log
Uh-huh.
mn,
Okay.
which is comparable to the two-stage binary search.
So both binary search approaches offer significant speed advantages
Definitely
over
a
brute force.
big time.
But I'm curious, are there any trade-offs we should consider when choosing between the two-stage approach and the flattened matrix approach?
That's a great question.
Yeah.
Um, while both are efficient,
Yeah.
there are some subtle differences.
Okay.
The two-stage approach might be a bit easier to conceptualize
Okay.
and implement for some developers
Okay.
because it follows a more intuitive step-by-step process.
So it's like breaking down a complex problem
Yeah,
into smaller, more manageable chunks.
exactly. The flattened matrix approach, on the other hand,
Okay.
might be slightly more efficient in terms of code execution
Okay.
because it only involves a single binary search loop.
So it's a trade-off between ease of understanding
Yeah,
and raw performance.
precisely.
The choice often depends on the specific needs of the project
Right,
and the developer's preferences.
exactly.
This has been such a fascinating exploration of binary search techniques.
It is a really cool problem.
It's amazing how we can leverage the sorted nature of our matrix to drastically improve search efficiency.
For sure.
But before we wrap up,
Yeah,
I'd love to get a sense of how these algorithms might look in code.
sure.
Could we dive into some pseudocode examples?
Absolutely. Let's translate these concepts into something a little more concrete.
All right, so let's make these algorithms a bit more tangible.
Yeah.
I always find that pseudocode helps me visualize the logic.
Pseudocode is a great way to bridge that gap between the abstract concept and the actual implementation.
For sure, for sure.
Yeah.
Let's start with the brute force approach,
Okay.
since it's the most straightforward.
Yeah. For brute force, we'd essentially use nested loops
Okay.
to iterate through every cell in the matrix.
Okay, so like our outer loop would go through each row.
Right. And the inner loop would go through each cell within that row.
Okay, something like this.
Hmm.
For each row in the matrix,
Yeah.
for each cell in that row,
Right.
if the cell's value equals our target,
Yep.
we've found it.
We found it.
And we can return.
Exactly. And if we reach the end of our loops without finding a match,
Yeah.
we know the target isn't present in the matrix, and we return false.
Simple, but as we discussed,
Yeah.
not very efficient.
Not at all.
Now, what about the two-stage binary search?
Oh!
That one feels a bit more intricate.
Let's break it down. Remember, the first stage is all about finding the potential row
Right.
using binary search on the first column.
Right. So we start by setting like a left pointer
Yes.
to a 0 representing the first row
Okay.
and a right pointer to the last row index.
Exactly.
Then we enter a loop that continues
Yep.
as long as our left pointer is less than or equal to our right pointer.
Right.
And within the loop,
Yeah.
we calculate the middle row index
Okay.
by averaging the left and right pointers.
Exactly.
Now we check the first and last elements of that middle row.
Okay.
If the first element is less than or equal to our target,
Right.
and the last element is greater than or equal to our target,
Yeah.
then we've struck gold. We found our potential row, and we can break out of the loop.
Exactly. But what if the first element of that middle row is greater than our target?
Well, then we know our target can't be in that row or any row below it.
Right.
So we update our right pointer
Yeah.
to be one less than the middle row index,
Okay.
effectively cutting our search space in half.
And what if the last element of the middle row is less than our target?
Then our target must be in a row below.
Right.
So we update our left pointer to be one more than the middle row index, again eliminating half of the remaining rows.
Exactly. This loop keeps going until we either find a potential row
Right.
or our left and right pointers cross, meaning the target isn't in the matrix.
Okay.
Once we have that potential row,
Yeah.
it's time for stage 2, a standard binary search within that row.
We set up new left and right pointers
Yeah.
for the columns within that row.
Right.
Calculate the middle column index and compare the value in that cell to our target. And we keep narrowing down our search within that row until we find a match
Yeah.
or determine that the target isn't there.
Now for the grand finale. Let's tackle the pseudocode for the single binary search on our flattened matrix.
This one relies on that clever mapping technique we talked about earlier.
Right. First, we need to calculate the total number of elements in our matrix,
Okay.
which is simply the number of rows multiplied by the number of columns.
All right.
Then we set our left pointer to 0,
Okay.
then our right pointer to the total number of elements minus 1.
Okay.
Just like a standard binary search.
Right.
We enter our loop, which continues as long as left is less than or equal to right.
Okay.
And within the loop, we calculate the middle index.
Okay.
But here's where the magic happens.
The decoder ring?
Exactly. We use integer division
Okay.
to find the row in our original matrix
Yeah.
that corresponds to this middle index in our flattened array. It's middle divided by the number of columns.
Okay, and to find the column, we use the modulo operator. It's middle modulo the number of columns,
Exactly.
with our row and column determined.
Yeah.
We compare the value at that location in our original matrix to our target.
Right. If it's a match, we celebrate. We found our target.
We did.
If the value is less than our target,
Yeah.
we update our left pointer to middle plus 1,
Okay.
shifting our focus to the right half of the flattened array.
Okay.
And if the value is greater than our target, we update our right pointer to middle 1, focusing on the left half.
Right.
This process repeats, narrowing down our search space until we find our target or our pointers cross, indicating the target is not present.
So that wraps up our exploration of searching a sorted 2D matrix. We've delved into 3 distinct approaches, from the simplicity of brute force to the elegance of binary search, both in its 2-stage and flattened matrix variations.
It's been a great discussion.
We've seen how understanding the structure and properties of the matrix can guide us towards much more efficient algorithms.
For sure.
And we've even peeked into the world of pseudocode, seeing these algorithms come to life.
A little bit. Conceptually.
Please conceptually.
Yeah.
Remember, the best approach often depends on the specific constraints and needs of your project.
Right.
But understanding these techniques gives you a powerful toolkit for tackling search problems in sorted 2D matrices.
Definitely.
Thank you for joining us on this AI.Code.Cast deep dive. Until next time, keep coding and keep exploring.